Hey folks, I got the last video for capacitance, and we're going to do a few more examples involving inserting dielectrics into part of a volume. Okay, so I got two examples for you. So the first example is, let's say you have a capacitor. Here it is, parallel plate capacitor, and I want to know, how does the capacitance change if I insert a dielectric such that the dielectric has a constant of that, and this takes up 1/4 the total distance between the plates. So if we call this D, then we're only taking up 1/4 D. And let's assume we're filling up the entire area though, okay? So what's our new capacitance compared to the old? So if the old was C naught, okay, so the old was C naught, what's the new in terms of the old? All right, so what we're going to do here is I am going to insert a piece of very thin metal. Now, you might recall from the last video that we are allowed to insert a very thin piece of metal, and as long as that A is very small compared to D, we ain't changing the capacitance any, okay? So by inserting that piece of metal, I haven't changed the capacitance at all. Well, now look what you have here. Okay, what you have is you have two capacitors. You have this one, we'll call it C1, that spans from here to here. And then you have this one, we'll call it C2, that spans from there to there. Okay, C1 has a width 1/4 D. C2 would have a width 3/4 D. And are they series or parallel? These two capacitors that we've created out of one. Well, if I were an electron and I was trying to get from one plate to the other end, I'd have to go through both capacitors. I have to go through C1 and C2. And is series. So C1 and C2 are in series. So what I'm going to eventually do is do the whole 1/over thing to get the net capacitance. Before I do that, though, I've got to write C1 and C2 in terms of C naught. So let's start with C1. Well, remember, for a capacitor, C is equal to, for a parallel plate capacitor, it's equal to epsilon naught A over D. Okay. Well, for C1, I haven't changed epsilon naught, and I haven't changed the area. Okay. I did change the D though. It's now 1/4 D, and I've inserted dielectric strength in there of that. Okay, so this turns into 4 times the dielectric strength times epsilon naught A over D. This was C naught. So this is 4 times dielectric constant times C naught. So C1 is 4 times the dielectric strength times C naught. How about C2? Well, for C2, again, you never change epsilon. It's a fundamental constant of nature. The area of those plates is the same, but now that is 3/4 D. Okay, so if I simplify that, I get 4 epsilon naught A over 3D, which is 4/3 C naught. Okay, so there's C1 and C2 in terms of C naught. Now, to figure out the total capacitance, the equivalent capacitance, I do the 1/over thing. So 1/over CEQ is 1/over C1 plus 1/over C2. So now we're just doing some math here. So 1/over CEQ is 1/over C1, which would be 1/4 strength C naught, plus 1/over C2, which would be 3/4 C naught. If I flip this over, I get that. Okay. Now, in order to get a sense of what this is going to be, you want to get common denominators here. So I've got 1/4 strength C naught plus 3 times strength over 4 strength C naught. So I get 1 plus 3 times the dielectric strength over 4 times the strength times C naught. And then CEQ, I just flip that over. So it's 4 times the strength over 1 plus 3 times the strength, all times C naught. So this is my equivalent resistance in terms of the old, my equivalent capacitance in terms of the old capacitance. Now, a note on this. Whatever answer I get, if I set the dielectric strength equal to 1, okay, in other words, it's as if I never added a dielectric at all, well, then my capacitance better turn into C naught. Is that true here? Well, if I put, for the dielectric strength, if I put 1, 4 times 1 divided by 1 plus 3 times 1 is 4 over 4, which is 1. And so that's true. So that's a way to check to see if the answer you got could even physically make sense. If you make the dielectric strength 1, your C should be C naught. Okay. My last example is similar, okay, but not exactly the same. It's actually going to be a little easier mathematically. Let's say I do the same thing, but this time I make a dielectric fill a bottom part of this capacitor. So let's say here's your 2 plates, okay, and you had a C naught, which was epsilon naught times the area of a plate divided by D. So this was D. And now let's say you stuff a dielectric in here like so. So it's got a strength like that. And this is 1/4 of the area of the plate. So it's still filling up 1/4 of the space, but in a different way. Okay, so what's our new capacitance now? Well, again, we got to look to see, hey, is this series or parallel? So if I were an electron trying to get from one end of this thing to the other, I can go through the air, or I can go through the dielectric, or is parallel. Okay, so you can go through one path or the other that's parallel. So we'll call this one up here, we'll call that C1, and this one down here, we'll call it C2. So C1, well, it's epsilon naught. Well, now I just got 3/4 of the area, and the distance is still the same. So that would be 3/4 of C naught, right? Because epsilon naught A over D is the original, and then I got 3/4 of that. C2 would be epsilon naught times, well, here I only have 1/4 of the area, but I then got to multiply that by the dielectric strength. Still the same distance, though. Okay, so how does this compare to the original? Well, the original was epsilon naught A over D, and so what I have is I have the strength over 4 times the old. Okay, now because these are in parallel, we just add them up. CEQ is going to equal C1 plus C2. So we've got 3/4 C naught plus strength over 4 C naught. And if you add those up and simplify it, you get 3 plus strength over 4 times C naught. So that is our new capacitance compared to the old. And again, you want to check. If you set the strength equal to 1, you should get C naught. Do we do that? Well, 3 plus 1 is 4 over 4 is 1, and you get the original capacitance. So when you're adding dielectrics such that they take up only part of the volume, you have to figure out, are they in parallel like this one, or are they in series like this one? Find each individual part of the capacitance and then add them appropriately, whether they're in series or parallel. All right, I hope that video was helpful, and thank you very much.